Oh, there we go. The transcription's right there. That might be distracting.
I don't see it. I
It's,
think it's so it only shows it for you.
yeah, it's on my side. Okay. Welcome, everyone. I guess, Ben, for all intents and purposes, you will be being trained today.
Yeah.
So, I guess try not to say the answers. We're going to talk about APC. Brianna has heard a little bit about this from last week, but we'll go into more depth today. First, let's talk about The Price is Right. The Price is Right, there's the bidding game part where you have to guess the price of an item. It's whoever gets the closest without going over wins. So, Brianna, if you, without cheating, would like to guess the price of this item, I'll give you 30 seconds.
Absolutely no idea.
You want me to stand in the background and yell numbers like the crowd does?
Might make it more immersive, I guess.
470, 27, $2. Like what?
You know, it looks like it costs $2. Yeah.
I didn't drop any hints there.
Yeah.
Don't read into that.
No idea. Yeah. Let's go $2. I know it's wrong, but
$2.
And in Price is Right fashion, I'm gonna go $1.99.
All right. And it's $29.99. So I guess Brianna wins. The takeaway here is APC is not unlike The Price is Right, where you're trying to optimize something while staying within limits. Now, The Price is Right, you don't know the limits, obviously, and that's the game. But APC will know the limits and it will optimize within those. So real quick, we need to talk about the difference between the DCS and APC. So DCS, the focus is more on one input, one output controllers. These are PID loops that are operating primarily on feedback. So you'll have an instrument like a flow transmitter and an output, usually a valve, and you'll have a controller that gets the input and then sends something to the output to control that input. So it's pretty focused. And while you could make it fancier than that, you can add feedback or feed forward control or have multiple outputs. It's generally focused on controlling one thing with a single other thing. Whereas APC sits on top of the DCS and it takes advantage of that DCS speed and focus individual controllers, and it looks at multiple things to control multiple other things. And so you've got a lot of inputs and a lot of outputs. The other thing that makes it a little different is it's model-based or predictive-based control as opposed to primarily feedback. It does have feedback, but it doesn't do as well on feedback control. It should be primarily predictive control, and that's where the models come into play. So what is a model? A model describes a relationship between your input and output, or PV, process variable, MV, manipulated variable. And so in this case, there's an example here where you have your MV or output, and it's stepped up, and then you can see the change on the PV, and then you can model that with certain model parameters, such as the gain. So the gain in any model describes that ratio of change. So how much does your PV change for a given MV change? That's a pretty big, this is one of the bigger model parameters used in APC, because APC looks at steady state time, which may be hours away. And so a lot of times, while time matters and is looked at, it's really the gains is the biggest impact because we're looking down the road after all this time has passed. But it also considers the time values in the model, which are the time constant, which is the time to change, but there's also the dead time, which is how long does it take to start changing. So APC, it has these models, model relationships between all the inputs and all the outputs. I shouldn't say all of them. It's got a matrix where you got quite a few filled in, but any output will have one or more models associated with it for the inputs it's controlling. So now we'll talk about some of the key parts of APC, which you should be somewhat familiar with after our presentation last week. So first, APC is made up of independent variables. These come in two different flavors. You've got your manipulated variables, again, the MVs, and feed forward. So first, manipulated variables. You also hear those be called MVs or handles most of the time. Those are the things that APC has direct control over. And so that's the specific differentiation here. It's what APC can move or control directly. So I'm going to use the car analogy that we did last week. And thinking real quick, what are some MVs handles that you have in your car? And we're recording this for posterity.
Speed.
All right. What are some other handles? And remember, these are the things that you have direct control over.
Radio.
Radio. Let's see. I don't know. I'm trying to think how you would do that one. I guess you've got control over the receiver directly.
The ignition.
Pedal.
Yeah, so gas pedal,
Steering wheel.
steering wheel. And I would say, actually, you do not, speed is not
No,
a
speed is
handle.
good.
But I would say cruise control set point is a handle. And so, yeah, so as far as MVs and handles go, I'd say steering wheel, gas, brake pedal, cruise control set point. Those are your big ones when it comes to driving a car. You might have a shifter if you're don't have an automatic. Feed forward variables. So these are things that you can't control but impact your process. So in a car, what are some feed forward variables that you want to worry about? Things that are on the horizon that are going to impact your MVs. So again, steering wheel, brake pedal, gas pedal, but aren't things you have direct control over.
Direction of the road.
Yeah.
Other cars in front of you or behind
Yeah.
you.
Yep. A hill. Yeah, a turn. Other cars on the road. Yep, perfect. Then you have one of the other major components is dependent variables. These are your control variables, or we call them CVs. These are the things that are directly impacted by your independent variables, such as the MVs or feed forwards. And thus, you can control them, or at least predict how they are going to be impacted by the independent variables. So in a car, what are those things that you, sorry?
Oh, speed. It finally gets
Yes.
to come back.
There you go. Yeah, so speed, maybe position on the road, distance between cars, RPMs, oil temperatures, all those things are impacted by your independent variables, but and therefore you can control them, but you don't have direct control over them. So then limits. All MVs and CVs have limits. They're generally high or low limits, but they could even be a target. And so another thing to think about though, real quick, is feed forwards don't have limits in APC. Obviously, because they can't be controlled by APC. So the other independent variables do, and the dependent variables. Again, we could talk about the car example. They may not be spelled out on a sign all the time, but what are some limits for a car? For the MVs for your car or CVs for your car? Do a little dance. Sing a little song.
Speed limit.
Yep, so speed limit, pretty clear one. What are some less clear ones that you got to worry about? So again, think back to your handles and your CVs. What are the limits for each of those? So brake pedal. You have limits on your brake pedal?
You have limits on your traction.
Yeah, there's yeah, that's kind of an indirect limit, I'd say. Even maybe a CV is your traction to the road and indirectly controlled. But yeah, you would have concerns with that. I'd say you're almost always at your lower limit with your brake, which is 0% brake. So there are physical limits to things. So a lot of times, the ideal scenario for our handles is the limits are the actual physical limitations of it. So if it's a valve, 0% or 100%, giving it the most degrees of freedom. And so for your car, you've got obviously something like speed limit. You might have high temperature for your engine oil, how far your brake pedal can move, or your gas pedal even. If you're a pedal to the metal type person, that's the maximum gas you can apply at a given time. So for APC, which this I feel like relates well to human driver, for your handles, you don't ever violate those limits on the handles directly, which it makes sense. You really can't if there are physical limits, like your brake pedal or your gas pedal has limits how far you can move it. You're not going to be able to violate those. But for CVs, those dependent variables, it is possible to violate the limits. Obviously, the speed can be violated maybe pretty easily in some cases. But so that's something important to note with APC is I'll get a lot of questions about why something's being ignored or it's outside its limit, and it's because that APC can make all those decisions. You might make the call to say, I am going to temporarily violate the speed limit here to get around this car or something like that. And so you're getting some other limit or helping some other limit with by violating another. And then we'll talk about optimization real quick. So every MV or handle has an optimization target called an economic objective. And so the target tells the system what to do with your handle if it's not constrained by anything else. So kind of what's the default state if you have nothing else to do? What should you be trying to do? There are 3 types of optimization targets. So first you've got maximize, which I think is pretty clear. Do as much of it as possible. So in your car, you might maximize your cruise control set point until you run against the CV limit on speed. Then you've got a minimization optimization, which will obviously the opposite, decrease as much as you can or use as little as you can. So in our car example, it might be minimize your brake pedal usage. You're not going to drive around with the brake pedal pressed down 25%. That would be insane. So you're trying to minimize that unless you need to use it for some other limit to keep it within control. And then you've got minimal movement optimization. So you try to not move it unless you absolutely have to keep a CV within limit. So in your car, again, that might be your steering wheel. You don't want to constantly be adjusting your steering wheel. That could be an uncomfortable ride. You want to minimize the movement. to keep you within the lanes. So recapping real quick, you got handles, control variables, limits, optimizations. Okay. So now you've got your handout, handout 1. I want you to take a look at it real fast, and you have a task ahead of you. So as the APC driver for this car, I want you to take a look at your handout and add on what CVs you need to worry about, and maybe make a note about their limits, and what MVs you need to worry about and their limits. And then for this scenario specifically, what is the main CV that you have to worry about? And what are the main handles to control that CV? I'll give you, I don't know, 30 seconds or a minute. And then you can share with the class.
Everybody stand up when you're done.
Oh man, you're right. I forgot that.
Raise your hand.
Oh, I'm supposed to interrupt you if you're almost done too. I forgot that part. Yes, let's call it done. Hey, so yeah, you mind sharing what your main CV is and your main handles? Maybe how the scenario would work out with your handles. Brianna.
So, our handles are gonna be, again, like gas pedal, brake, and steering.
Mm-hmm.
Because looks like we're trying to control speed, right? And also we have to go around a curve at a slightly lower speed.
Yep, you got a recommended speed limit for the curve, 25 miles per hour. And so as you're approaching your curve, as your feed forward is gonna predict your lane will deviate, your lane position will start to violate on the, I guess, left-hand side of your car. You're gonna start to get outside the lane. And so as an APC controller, you're gonna start to turn that steering wheel. You'll probably let off the gas. And if that's not enough, you'll start adding some brake. And so while you're doing this, you're trying to minimize the use of brake, so you don't have to use gas again, unless you have to. And then also minimal movement on your steering wheel, but you still have to move your steering wheel in this case. Yeah. All right. How long has it been? It's been 90 minutes. I'm just kidding. We'll talk about the web interface, which granted this will be, I guess it'll help you to go look at it with the other in the boardroom if you were to do something that involved APC. We'll go through it though so we can record it for anyone else that might want to watch it. But we'll talk about each of these sections here. So you've got, again, independent variables, which are split up to your MVs and feed forward variables. The feed forward variables, you could tell, are a little different from the MVs, even though they're in the same section, because they don't have the limits or anything else. They just have on off essentially, as far as interaction goes. And then you got your dependents, the control variables on the bottom half here. We'll look at the combined status real quick. So there are quite a few, there's a whole column devoted to this. And so when you're looking at APC, there'll be colors all over the place. These are what the colors mean. So blue is at the limit or target. So again, high limits, low limits, ramp, external target. Ramp is the target for levels, which are called ramps in APC, things that are integrating. They never level out. They will continue to increase or decrease unless you make a move. So you get combined status of yellow, which for a control variable is giving up on a limit. And for an MV shows it's at a DCS limit. So that might be you've reached that 0%, or you might have a clamp on a valve saying you don't want it to go over 75%. And so you've hit it, and that'll read as AWS high or low, which is a wind up status. Green, so for CVs, that's giving up on a target, but it's within the limit still. So you got high and low limits, but it's the targets between those. And so it's not as optimal, but it's still within the control range. And then for MVs, it's all over the place. This represents your minimum movement optimization target, or ROC up or down, ROC being rate of change. So it indicates if you are, it's a tuning parameter we put in there that it's only allowed to move so much for a given time range. So you might hit that. Then you got light red or pink, which is out of service. Operators or engineers can turn it off. And then red is bad. So that could indicate complete loss of connection. If they all go bad, it would show that it's lost connection to the DCS. But if it's just one that goes bad, it's probably because it's outside of the validity limits. And so each of these variables has validity limits that tell APC if it's outside this range. Don't use it. That's bad. The other thing to note with combined statuses is every MV, every handle should be constrained by something. Now, it could be its own limits. It could be the CV limit. And so you should see an equal number of limits, essentially, as you do MVs. So in this case, we have 7 MVs, and we see 7 blue highlights. So you got 2 MVs at high limit, 3 MVs at low limit, and then you have 2 CVs that are at their targets, essentially. And so those, just by looking at this, you could maybe guess what each of these is constrained by. Obviously, the MVs at their own limit are constrained by their optimization target limits, but the other 2 are constrained by those CVs down below. So we'll talk about service requests real fast. There are 3 different options. So off is completely ignored. It's similar to bad in the sense that APC ignores it, doesn't use it for control or prediction. On, fully used for control and prediction. And then prediction, this is where it gets a little confusing. So for MVs, if you're going to manually manipulate one of your MVs in the DCS, or just put it in auto in the DCS and adjust the set point yourself, you should put it in prediction mode because then APC could see those moves and estimate the impact on the other variables that it normally is used to control for, and then it can use the other handles still in service to control it. For CVs, APC will predict where the variable is going to go, but it doesn't control off of it. So it's just a way to see what's going to happen without controlling it. We'll talk about the optimization real quick. So you could see optimization in the strategy tab, which is also available in the control narratives. So the strategy tab, I'll ask Brianna, do you remember what process gain is? Or a gain?
Yes. Yeah,
Okay,
we've got the change in PV over MV, right?
awesome, yes. And so positive gain means that they correlate. They've got the same, they move the same direction. Whereas negative means there's an inverse relationship. Solid and just means, when you're reading this table, solid means that it favors the economic objective. So if it's maximizing, it will be solid if it wants to move it up, and the inverse for minimizing. So if we look at this case here, the case in UR2, you can see the manipulated variables make up the columns, or sorry, the rows, and the CVs make up the columns. And the strategy or optimization target, economic objective, that is indicated by that very left-hand side of the MV. So FFC 5024 SV is trying to be maximized by APC. So in this case, you can see you've got your CV of FI 5041. When it's at its high limit, indicated, the column's kind of split in half. The high limit's on the very right side. It will decrease 5024, and that does not favor the economic objective, so it's empty or hollow. If it's at its low limit, it will increase 5024, which favors the economic objective. And you can see it's positive gain, which means they move the same direction, and so it's blue. So expanding this a little bit, we have LI 5915. So I'm going to ask you a question, and you can look at it and see if you can interpret what it will try to do. So let's say this LI 5915 PV is at its high limit. What will it use to control that high limit? We can step through this. I want you to look at it first, see if you can interpret what it will do. I guess first, which handles does it have available to it based on the strategy table?
But all of the stuff on the left-hand side.
Yeah, yep. So in this case, it's all of them. And I will say it will, the way that this works, again, if you split the column in half between the low and the high half, it will do it in order of those numbers. So first, it will do 5906. And then if it's still having trouble keeping it within the high limit, it will move 5965. And if it still has a problem, it will move 5133. And you can see we can make some intuitive guesses as to why the order is set up this way. So the first two, that direction favors the economic objective. And so it's a tuning decision as far as which one is done first, and that could be for a number of reasons. And then the third choice, because it's set up for minimal movement, we don't want to move that one unless we have to. And so that one first. But for the low limit, which one does it use first?
It uses that 5133.
Yeah. And so it's kind of, now it's almost the opposite here. And the reasoning might, again, it'll be a tuning decision as to why we do that, but because because none of them are favored by the economic objective in that case, it is kind of a, hey, which one do you want to move first? And then we'll set that up. So expanding even more, you could see all three types of optimization here. We got the maximize with the plus, minimum movement equals, and then minimize with a minus. Real quick, we'll talk about looking at the models. So there's a model tab on here as well. And if you hover over or double click it, you can see the gain. So again, the gain tells you how much it moves based on the change on the MV. In this case, LC 5139 MV will move 0.52 for every 1 unit change on 5133 SV. There's a gain multiplier though, which is kind of uses a tuning parameter to adjust the model. And you can see that on the top right, the dotted line has been a gain that's been multiplied. And the effective gain shows what that multiplied value is. In our case, that's highlighted here. The gain multiplier is 1, so it's just the same. But the number that's displayed on the graph, that 4.16, that is the typical move multiplied by the effective gain, which is confusing. I wish they just showed the gain on here, but that's how it's set up. The typical move, I'm not entirely sure where it comes from. It's something that's, when you run and create these models, APC somehow generates that based on, I'm guessing, the data that shows how much it moves, generally on average. Oh, time to dance again. So we'll go real quick and we'll talk about troubleshooting. So a lot of times when we're talking troubleshooting with APC, it's a question of, why is this CV outside of its limit? Or why is this MV moving? Or why is this MV not moving? So something you can do is, if you click on any variable, it opens this menu. You click Control Objective, and it should tell you what it's trying to do. I will say that sometimes this breaks. It's unclear why, and it doesn't show any information. But usually you could get information out of here. And in this case, you've got 5965 showing not constrained, and it's not being maximized because of 2 different categories. So category 1, relevant CVs. So it's showing that, well, you've got 2 compartments that are above their high limit, and you've got this LC 5136 MV at external target. And then you've got MV constraints, which show the other MVs that could help out, but they are constrained themselves. And so you've got 2 TCs, temperature controllers, associated with those compartments. They're at their low limits already. So they are essentially minimized out. They can't help. And then HC5004, that would also help out those temperatures, and it's at its high limit in this case. So something you should always do is you should come here, look and see what it's held back by, and then confirm that all those limits are set properly. So generally, if things aren't controlling well, it's because limits are set too constrained. So if you think of your car example again, if you're going to take that 90-degree turn, but you have some artificial limit on your steering wheel that you're only allowed to move at 5 degrees, you're going to have a hard time keeping yourself within limits and controlling. And so you need to give yourself more room on your handle to control, or make your CVs less constrictive, which you don't always have the option to do. Sometimes the CV, it's like, oh yeah, you have to stay within this limit. And so you need your handle to have as much room to operate as possible. The other thing to check in combination with the control objective is the strategy tab. So I'll use both of those things. In this case, again, if the temperatures being above their high limit, I would try to see what other things are used to regulate the temperatures and then look at the control objectives for that. And again, check and make sure everything is within limits. If all relevant MVs are online, so you might have something that's off, that could help out as well. But if all relevant MVs are online, all limits are good, and things still aren't working properly, then it's likely we're missing a handle or something else in our model to help us control it. And that's generally the case where if we are moving some handle and we don't want to, it's because there's a different handle that should be moving, but we don't have it in APC. And so we should get it added. All right. We're going to do a bigger practice now. So real quick, cooling towers. Hot water comes in the top, air gets sucked through, some water evaporates, which cools down the remaining water, which is then circulated through the process again, and it gets hot. Because you're evaporating off a bunch of water, you need to make up more water to the cooling tower, keep it full. And also because you're evaporating water, you're building up dissolved solids, and so you need to blow down to keep conductivity under control. So for your second handout, let's see, let me pull up my instructions here. You're on a different slide. Yes. For your second handout, I need you to, I'd like you to identify control variables, handles, MVs, maybe even a feed forward, and then make a basic strategy table for one of those MVs. One MV CV relationship. Oh, and also identify the optimization target. What did he always say? How can I clarify the instructions before you get started?
Before we get started.
Yeah. Yeah, feel free to ask. There's a lot of, I should probably figure out a way to list these things somewhere. But yeah, MV, CVs, maybe feed forward, make a strategy table, show the optimization target. So just
See you in a few
arrows.
hours.
The what?
See you in a few hours.
Yes. I'll give you a minute or two here. I honestly don't know how much time you need. I guess in this case, you could stand up when you're done.
Keep the lights on.
Yeah, exactly.
I'm not actually done.
Oh, okay. Those lights.
Mm-hmm. Surely there's a way to turn that on.
I guess the one problem with being remote when you guys are in there is I have honestly no idea if it's a good time to interrupt you or not.
Yeah, I know.
How's it going?
That's true. It's when they pick up their phone.
Yeah,
Yeah. That's yeah, that's a good point. understanding. All right. Who wants to share first? I'm curious what you guys have done. You can just walk us through your CVMV strategy table. Let's have Brianna go first. The last person to drink out of a water bottle, or yeah.
You know, I just drank.
Yeah.
So this is the part where I was getting a little bit confused with my MVs and my CVs. But it
It's
looks
fine.
like
We are learning. It's
yes.
a no judgment zone.
So it looks like we're trying to control the level and I think conductivity, I'm guessing from the analyzer and
Yeah.
and then temperature, is that something that we're doing? I don't know. I see ambient temperature.
Yeah, what did I put on here? I don't even remember. Maybe I should add a note for the AI one. I feel like I was going to do that and I forgot. Anyway, yeah, so ambient temperature's on there. Ambient temperature, probably more of a feed forward because you can't control that.
Yeah, but
But you're right. So we're trying to, yeah, we've got AI1, LI1, LC1, HC1. So you identified, let's see. Sorry, you want to list off your CVs again? You said conductivity level.
yeah, conductivity and level and I guess we're affecting those with the amount of makeup or blowdown that we have. So LC1 and HC1 are
Yep.
one.
Yeah, that would be totally legitimate way to do it. Do you have a strategy table?
I'm a little bit confused about that part.
That's fine. All right, Ben, what do you have?
So I'm also using kind of a strategy table. I've got feed forward from HC1, so when it opens, go ahead and open LC1 as well to make up for the loss level during the blowdown.
Nice. Yeah.
And then you could actually kind of control the temp if you had, I was just thinking about that. If you had a temp of the water you're trying to control, you could actually use the blowdown as a means to bring in makeup water that's cooler.
Yeah. Just straight up cold water.
Yep.
Yeah.
Yeah.
And of course, controlling level with LC.
Yeah. Let's see, did that? Oh, that's interesting. I used my arrow keys, didn't actually move anything. All right, I'll share what I set up here real fast. So I said HC1 is my MV exclusively, and I was gonna minimize it. I didn't put a minus on there. I shouldn't add that. Now I didn't necessarily. You could use LC1 directly. Like I said, I think it's a totally legitimate way to go. The reason I didn't is I was thinking LC1, and the example I have here is more of a, it only impacts the level mostly. You could try to use it to control conductivity, but it's not going to have much control on conductivity compared to the blowdown and just evaporation. So being a one-to-one relationship, one input, one output, I just said, let the DCS control that. But you could control it in APC too. It would be something APC could totally do and handle, and like you guys both used, it would work great. Let's see. So HC1 minimize for CVs. I put LI1, AI1, and LC1 position, though I probably wouldn't use both LI1 and LC1 position. I'd pick one, probably LC position, and let DCS worry about the level, and let APC worry about if my level is getting off control. Because the best indication of off control would be if my valve's all the way open or all the way closed, I know something's going on here. So then if we'll go to say the conductivity is high, then I would increase HC1 to remove solids. And if it's low, then I would decrease HC1. If my valve position is at its low limit, I would increase HC1, which would cause the level to drop, which would cause the valve to come open. And then if LC1 is at its high limit, which is probably close to 100%, then I would probably put it like 90% just to be safe, give it some buffer there. Then you would want to decrease HC1. And then yeah, temperature feed forward. As the ambient temperature goes up, your evaporation rate is going to increase, which is going to increase your conductivity. And so you're going to need to increase your blowdown to account for that. And I still don't know how to close one of these meetings. So
I like the use of LC1 there
yeah,
as a feedback to that positioner.
the big thing, I guess, for APC is just like the DCS in that there's not necessarily a right answer or a wrong answer. It just depends on what your main objectives are, the easiest way to do that. So thanks guys for coming. Do you have any other questions or things you want to talk about?
I don't have my star clappers with me.
Dang. You brought that whole box back, right? On
I
your
did.
motorcycle.
I did. Those bungee straps are fantastic.
Yeah. Yeah, well, Brianna, what'd you think? Understand APC a little better?
I think so, yeah.
Probably need to understand the DCS a little better too. But
Have you seen the DCS training one?
probably not.
We can do that one too.
Recorded those, right? Or do we just do
Yes.
the DCS block one?
I think, well, the DCS block one got recorded for sure.
I'm not sure if the other ones did, but because there's the PID one,
Yep.
and then there's the general blocks one. I don't know. You probably haven't taken controls yet, huh?
So I've taken part of controls. I had to leave part of the way through this semester, which is
Oh,
made my year a little bit funky. So like I knew a little bit, but not as much as I probably would have if I had finished the class. So
yeah. You're fine. I mean, again, you have the basic idea there. That's the biggest thing.
I still
And
have
dead
an
time.
OpEx books here, so
Oh yeah.
yep.
I guess we could probably stop recording. Goodbye, those watching the recording.